At the Farnborough Air Show in 1952, a brand new aircraft was shown straight off the secret list. The aviation world was startled when test pilot Wing Commander Falk put the aircraft through some outstanding maneuvers. The Avro Vulcan, the world's first delta-wing bomber. For 12 years, from mid-1957 until mid-1969, a force of British-built bombers armed with nuclear weapons not only formed the core of the Royal Air Force, but also represented the foundation on which the national defence as a whole rested. At the close of World War II, there was little hesitation about the need for Britain to develop the use of atomic weapons. And since British scientists had played an important part in the American wartime atomic program, Britain now had access to the technologies involved.
Now, the first Vulcan flew from this factory on August the 2nd, 1952, and it was piloted by a gentleman called Rowley Falk. He was the superintendent of flying, and he flew it over Cheshire and the Lancashire area for 2.5 hours. And it stopped the whole of traffic in the Manchester, Cheshire, Lancashire area because nobody had ever seen anything like it. It was terrific. And that's how the Vulcan came to being. A week later, he took it down to the Farnborough Air Show and he rolled it like a fighter. Unbelievable for a 70-odd ton aircraft, which it is. I mean, it is 70 tons unladen, it carries 30 ton of fuel, and when it's fully laden, it's over 100 ton, which I think is a marvellous achievement.
The strategy of air power moved into a new era. There followed an uneasy peace of the late 40s and the Cold War of the 50s. An iron curtain cast its shadow across the world. Democracy faced new dangers in Europe and Asia, and tensions continued to mount, though statesmen struggled to preserve the peace.
We found that we once again hold the key to opening.
But in those years, we saw evidence that others had not been idle in building up powerful forces of destruction. Thanks to the vision of air staff, Britain had not been left behind. They saw the need for aircraft able to carry even deadlier bomb loads, higher, faster, and further than ever before. It was in January of 1947 that the specifications for such a bomber and orders to tender was received by Avro & Co. Limited. Avro's designers had already examined the problems of creating an aircraft with the very ambitious performance requirements demanded by the ministry. But now it had become a firm agreement. Roy Ewins, chief designer, explains the problems involved. A very large conventional aircraft with swept wings seemed the obvious solution.
But it just would not do. The wings were too large and too heavy. An alternative concept we explored was the tailless aircraft, but here again we were beaten by weight. The specification demands a very high cruising speed, close to that of sound, and this means that the wings must have a low thickness chord ratio, a low wing loading, high sweep back, and low aspect ratio. Our project studies led us eventually to the triangular or delta planform, which gave the best combination of these features. The delta has other important advantages. The low wing loading gives reasonable takeoff and landing speeds and distances without using flaps or other complicated high-lift devices. The low aspect ratio gives excellent flying qualities in spite of the high sweep back. The wing structure is inherently stiff and strong, and there's ample space within it for housing the power plants, the fuel tanks, and the undercarriage without prejudicing the clean aerodynamic contour. The weight and complication of a tailplane are avoided. Longitudinal control is provided by elevators at the trailing edge of the wing. The more we studied the Air Ministry specification, the more the Delta seemed to be the best answer. Finally, a decision was taken. Avro would build a Delta.
In the company's wind tunnel at Woodford, the aerodynamic characteristics of the new planned forms were thoroughly investigated. So little was known of the practical behavior of the delta wing that an unusual decision was made. Experimental aircraft, exact third-scale replicas of the new bomber, were built for research into the handling characteristics of aircraft of this shape. It was at this stage, early in 1950, Mr. Rowley Falk joined the company. Mr. Falk probably knew more about delta wing aircraft than any other pilot. He began development flights at a crucial stage.
2 third-scale research aircraft were built to try out the flying characteristics for the projected bomber. The 707A was made for high-speed flying, and the 707B for low-speed handling. The 707B was built first. As soon as we were thoroughly satisfied with the low-speed handling of the Deltas, I started on testing the high-speed aircraft, the 707A.
It was the first time any delta wing aircraft had flown in Britain, and it aroused great curiosity which wasn't entirely confined to the aeronautical profession. They were busy and exciting days back in 1950. For the small Avro Delta team, life seemed to revolve round a little hut on the Ministry of Supply's research establishment at Boscombe Down. During all the Delta test flights, automatic cameras recorded readings on the dials of the 24 instruments. The film was removed for immediate development after each flight so that the readings of every instrument at known intervals could be examined. Later, a technique was developed in which instruments made their own records automatically. While this research was going on, a full-scale mock-up of the Vulcan was built. In addition, the company installed several new test rigs. In this rig, the power-operated flying control system had been laid out exactly as planned for the aircraft. Typical movement applied to the stick by the pilot could be reproduced, and the responses of the controls analysed. On the same rig, large lead discs represent the mass of the ailerons, elevators, and rudder. Hundreds of hours flying could be condensed into a short space of time. On the hydraulics test rig, the undercarriage was tested under loads representing conditions of actual flight. The bomb bay doors were opened and closed hundreds of times, so that the way they work was thoroughly tested before the aircraft flew. Another test rig was built to examine engine bay installations and to check pressures and temperatures. Wool tufts attached to the intake ducts were used to study the airflow. It was found that the Vulcan's long intake tunnels smoothed out irregularities in the airflow so that each paired engine received an identical flow of air. Because of the extreme altitude at which the Vulcan was to fly, some special research was also needed on the pressure cabin. This was completely immersed in a water tank and water pressure applied to the inside. These tests were a guarantee of the crew's safety. Special research was also conducted on the window glass, which was tested to destruction. Glass panels were mounted on a frame which represented the windscreen, and the assembly bolted to the steel cover of a pressure vessel. A preloaded dial gauge was connected to the surface of the glass by a fine wire. As the breaking point is approached, the fluid can be seen escaping from the plastic inner layer between the glass laminations. A complete aircraft was also built for structural tests and successfully withstood loads exceeding the designed requirements. Saturday, the 30th of August, 1952. The first Vulcan prototype was ready to fly. 4.5 years of intensive work had gone into the making of this aircraft. Unlike the launching of a ship, the first flight of an aircraft is not a ceremonial event. The only people present were a few of the firm's staff, to whom this day meant so much. It was a huge aeroplane and quite unlike anything of its size that had flown before. But its test pilot, because of his experience with the 707s, was full of confidence. He'd already flown many hours in deltas.
Car 698. Read.
698 Woodford Tower, reading you loud and clear.
698, taxi clearance.
Clear to taxi, runway 26.
Take off.
698 Woodford Tower, cleared for takeoff.
I was actually down there on the Saturday morning waiting for things to happen. He'd given it a whirl the Friday night. It frightened AQD to death. Hadn't taken it, but on Saturday morning he took it. And as he came to me, I saw the nose wheel lift. I saw the front bogies lift. And he was right opposite when the last bogies just trembled away. So I saw the first half inch of the first flight of the first Vulcan, and I cried like a baby.
Only 3 days after its flight, the prototype made a dramatic appearance at the SDAC display at Farnborough. Falk flew it alone. This 50-ton aeroplane could be flown single-handed. It's one thing to build a prototype, but quite another to put the aircraft into production.
Yes, production is the key word now, and I don't think that should bother us too much. We have a staff here of about 9,000 people at the moment. We did have about 40,000 during the war, and we have, of course, a very efficient and able production and pre-production administration.
The production of the Vulcan had been planned from the time the aircraft was just a pencil outline. 50,000 special tools had to be made to put the first squadron of Vulcans into the air. Shown here is a universal rib assembly rig. Each rib, exactly made, had its place in the wing assembly rig. All Avro's press capacity was used to hasten production. In this 5,000-ton rubber press, large parts could be produced in one operation, therefore lowering costs. A special procedure was adopted for making a curved spar, one of the few universal parts in the structure. This machine was designed and made by Avro to roll the spar to contour. These are all existing techniques, and to remain in the forefront, new ideas must be developed to improve continuously the performance of aircraft. At Avro, much time and effort had been spent on evolving lighter and stiffer structures. This honeycomb sandwich, which has these qualities, was in production for the Vulcan. Here you see the manufacture of a typical honeycomb sandwich panel. The assembly is clamped together and placed inside a bag from which the air is evacuated. The adhesive, previously applied to the inner surfaces of the sheets, is now cured in an oven. So this undercarriage fairing panel, for instance, is much lighter and much stiffer than one made by conventional methods. And so the Vulcan goes into production. Bombing up on the Vulcan is both speedy and simple. The Avro twin-jack hoisting system enables the entire bombing up procedure to be conducted from the ground. The rams of the jacks inserted at each end of the carrier are extended until they engage attachments at each end of the bomb arches. The jacks are now retracted, taking the carrier with them. This Avro method of bomb loading eliminates hoisting from above or standing on the aircraft wings or fuselage with the risk of damaging the aircraft's skin. The fact that the whole operation can be done from the ground underneath the aircraft means that bombing up can be done in all sorts of weather and at night without special lighting above the aeroplane. The armourer too can observe that the bombs are suspended absolutely evenly without any upset in balance. As soon as the carrier is locked in position, the jacks are removed. As many as 10 bombs can be loaded into the Vulcan on a single carrier. This is another notable Avro achievement. The first carrier able to hold more than 2 rows of bombs. The bomb bay of the Vulcan holds 3 such carriers. This means the single load of the Vulcan can be increased from 21 1,000-pound bombs to 30 1,000-pound bombs. A load of 60 bombs can be carried by 2 Vulcans instead of 3. Ingenuity with excellence of aircraft design have combined to produce a bomber with immense striking power. All the ability to design and build a beautiful-looking aircraft which meets its original specifications isn't enough in itself. Peter Sutcliffe, the company's chief aerodynamist, explained how new operational requirements were met by the Vulcan without major redesign.
Flow separation is one of the most difficult problems of transonic flight, and solutions can only be obtained by close attention to the shape of the wing, both in plan form and section, especially in the region near the tips. The basic wing of the Vulcan has been modified by increasing the chord by about 20% in this region and extending the cord forwards and downwards towards the local incident flow. This simple modification allows the air to flow smoothly over the upper surface of the wing at incidences far greater than is possible on the basic Vulcan. All production Vulcans are fitted with this modified leading edge and are capable of using to full advantage those engines now being developed, up to and including 13,000 pound sea level static thrust. If we are now to consider the benefits in terms of increased altitude that are available from engines of even greater thrust, then we must consider more far-reaching modifications. This diagram shows the extent of such modifications, but even here it will be seen that a very considerable part of the major structure is left completely unchanged. The only portion of the wing affected by the modifications is that outboard of the elevators. It is the comparative ease with which modifications of this kind can be introduced that gives the tailless delta layout its great development potential, and once again demonstrates the basic suitability of the Vulcan for a high-flying, fast bomber.
In order to equip their engineers with the fundamental research into the problems which face them, the company invested large sums of money in capital equipment. Thorough and painstaking studies of the effects of temperature were needed. The high-altitude pressure chamber had been installed to reproduce the extreme conditions of pressure and temperature in which not only the Vulcan, but other aircraft of the future would fly. The operation of aircraft mechanisms can be studied in this chamber at a temperature of -70 degrees centigrade and at pressures equivalent to an altitude of 75,000 feet. The Avro flutter and response simulators can tell aircraft designers precisely how their projects will respond to control movements or disturbances in the air when it flies. Here, the simulated disturbance to an aircraft damps out quickly. At a different configuration, the same disturbance leads to a nosedive. Added to these aids is the very latest digital computer popularly known as the electronic brain. The problems translated onto perforations on a roll are fed into the computer. Calculations which would have taken a month could be condensed into a matter of minutes. Even the models used in supersonic wind tunnel research were built in steel and finished by hand. In this tunnel, speeds of up to Mach 1.6 could be reached, and Avro built a third wind tunnel for research into Mach numbers as high as 3.5. The Schlerum apparatus is moved into position. Observers wait for the shock wave to appear on the Schlerum screen. And so the Vulcan joined the Royal Air Force. What began as a pencil outline in the design office of Avro became a formidable weapon in the hands of specially picked crews of Bomber Command. The Under-Secretary of State said that the Vulcan is equal to, if not better than, any other bomber in the world. These aircraft were followed by a later version, the Mark II Vulcan. This variant had increased all-round performance in range, speed, altitude, and carrying capacity. The Vulcan's striking power was increased by the Avro standoff bomb, perhaps the most important factor in the vital role this aircraft was destined to play. This guided weapon, designed and built by Avro, gave enormous tactical advantages. The Vulcan indeed became a fully controllable missile launching platform. The Vulcan held a key position in Britain's frontline defence. The RAF now had an aircraft with a great tradition behind it and a great future before it.
The first batch of Vulcans that went into service was 12, and they went down to Lincoln into what we call the 40 squadrons. And then after that they were based, of course, around Lincoln, Conisbee, Waddington, Scampton, etc. Most of the Vulcans were based in the Lincolnshire area to start with, and then some were dispersed abroad in Gibraltar and I think some in Malta.
The Vulcan entered service with the RAF in May 1956 with 230 Squadron, and later number 83 Squadron at Waddington. It also went on to equip numbers 27, 44, 50, 101 and the famous dambusters 617 Squadron. The RAF Vulcan was designated the Vulcan B Mark I. With the advent of the new powerful Olympus 200 engines, which were first flown on the Vulcan B-1 at the 1958 Farnborough Air Show, the development of the more advanced Vulcan B-2 was made possible. This degree of extra power would give higher operating ceiling for the Vulcan and would make it possible to carry a greater payload, such as the new Blue Steel standoff missile and the new Skybolt missiles. Avro began tests on the Skybolt for the USA. The data was fed back to America. The behavior of the missile during release was observed, and this indicated very satisfactory characteristics. Flow patterns in the region of the Astro tracker were investigated, and use was made of the aircraft. On the 17th of April 1961, the first of the 8 dummy missiles arrived from Douglas on schedule. The missiles were fitted with core cylinder flare shape of re-entry vehicles, which were now superseded by the sphere cone shape. Although the launcher had successfully passed all its tests in the USA, further tests were made to ensure the combined deflections of the launcher and the Vulcan pylon did not interfere with the operation of the release system and would not cause inadvertent release. On the 26th of September, the missiles were refitted to the aircraft in preparation for the compass swing, and the aircraft was towed out to the compass bed. Although the dummy missiles were not representative of the operational Skybolt from magnetic considerations, they contained large masses of steel which were expected to give more compass deviation than the final Skybolt. Wing-tipped cameras were also fitted during the swing to ensure that despite their close proximity to the compass protectors, they would be accepted for the trials. Neither missiles or cameras produced excessive deviation, and the errors were easily compensated by the normal adjustments on the compass. No difficulty was anticipated on normal operations, and arrangements were made to carry out a full compass survey when representative missiles were available. On the 28th of September, the aircraft was cleared for flight. But in view of the extensive work carried out on the aircraft since its previous flight, it was considered prudent to make an initial flight without missiles, but with the pylons fitted. The flight would give an indication of possible effects of aircraft handling on flying with missiles. The flight was very successful and revealed no change in handling. On the following day, the 29th of September, the missiles were fitted to the aircraft. The necessary safety checks on the release system were made, final inspections of the installations were completed, and the aircraft cleared for its first flight, carrying 2 dummy Skybolt missiles. The program for the first flight was to investigate the effects of the missiles on the handling characteristics of the aircraft, and if the pilot was satisfied, to increase speed. Mach number and altitude to the limits of the flight clearance certificate, that is, 300 knots, as indicated Mach number, and 50,000 feet altitude. On the 29th of September, the aircraft took off on its first flight with missiles, 2 days ahead of the program date. The pilot's report on landing, after a flight of 1 hour and 15 minutes, was that the full envelope had been covered and that it was virtually impossible to distinguish any difference in the handling of the aircraft. During the 7 subsequent flights with 2 missiles and 2 flights with 1 missile, the full range of flight parameters had been fully investigated and instrument readings obtained to show that there were no problems in the operation of the Skybolt missile. During the early 1960s, air-to-air refueling, which had been the subject of desultory experiments since before the war, was introduced into the RAF's V-Force, not only to extend their range, but also the pre-positioned in-flight tankers could take the place of costly intermediate landing posts. Many spectacular long-distance flights with air refueling emphasized the Vulcan's incredible ability to reach remote places of the Earth in less than a day. As, for example, the 8,500-mile non-stop 17.5-hour UK Karachi and return flight by a Vulcan from 617 Squadron, followed by a Scampton to Sydney non-stop flight in 20 hours 3 minutes. Others took part in Operations Sky Shield and Western Ranger, which were mainly long-distance flag-waving exercises and training flights, often in partnership with the United States Air Force. In 1962, one Vulcan from numbers 27, 83 and 617 squadrons from Scampton flew to New Zealand to join in the Royal New Zealand Air Force's 25th anniversary celebrations. On their return flight, 617's Vulcan established a Goose Bay to Scampton speed record of 3 hours 46 minutes, an average speed of 656 miles per hour. In May 1962, an incident occurred which gave credence to the doubts that the RAF were having about the future of the V-Force and the primary launch platform for nuclear warheads. The American pilot in a U-2 aircraft had been shot down over Russia. This was a clear indication of the rapidly growing Soviet capability in surface-to-air missiles. Such defences would very soon be overshadowing the viability and effectiveness of the V-bombers. The Royal Navy had been given a directive that Britain's nuclear force would be based on Polaris submarines. But it was going to be essential to keep the V-Force operational for 5 or 6 years ahead until the Polaris fleet was in service. The only practical alternative to the high-level attack profile which had been developed was to operate the bombers at very low level. By operating high-speed, low-level attacks, the V-bombers could still make their way to the target by flying underneath that radar defense. So, despite all of the previous high-altitude training that had gone before, pushing the aircraft to their limits, the Vulcan crews were given quite different challenges of low flying on high-low, high sorties. The white paint scheme was also changed to the more conventional camouflage finish. The Vulcan squadron adopted a new system of readiness, which meant that each squadron kept one crew on alert at any one time, known throughout NATO forces as Quick Reaction Alert. These crews were at 15 minutes readiness. However, the RAF V-bombers crew perfected this to such a degree that at any given time they could be airborne in under 4 minutes. Another important factor for the Vulcan also took place at this time. The aircraft were used as test beds for engine development of future aircraft. With the test engine being mounted in an underslung pod, these Rolls-Royce and Olympus engines were tested for experimental aircraft, including the ill-fated TSR-2. Then they were assigned to the Concorde development work, completing over 400 hours with Olympus 593, before the supersonic Concorde prototype flew. The Rolls-Royce Turbo Union engines of the Tornado were also tested on a Vulcan. In 1968, the Polaris and the Vulcan B-1s were taken out of service and the squadrons were re-equipped with Vulcan B Mark IIs. Whilst some of the Vulcans took on a more conventional bombing role, others were modified for long-distance strategic reconnaissance, previously carried out by the ill-fated Victors, most of which had been retired early for structural problems caused by low-level flying. Throughout the 1970s, detachments of Vulcans were based with the Near East Air Force in Cyprus. Others ventured further afield on major military exercises, such as the United States Air Force Strategic Bombing and Navigation Competition in Louisiana, competing against B-52s and F-111s. The Vulcans won 2 out of 3 possible trophies. When the first of the Vulcan B-2s were delivered to the RAF Regiment's firefighting school at Catterick on June the 9th, 1981, it marked the beginning of an end of an era, the start of the Vulcan retirement program. The fate of this aircraft was now firmly sealed. However, in the twilight of its service career, the Vulcan, for the very first time, was to fulfill the very role it had been designed for: the live bombing of an enemy target. The Argentinians were the enemy, the war was in the Falkland Islands. On May the 1st, 1982, operating from Wide Awake Airfield on the Ascension Island, 2 Vulcans took off en route to Port Stanley Airfield. One Vulcan turned back because of equipment failure, but the other flew over 3,400 miles, aided by refueling. to successfully drop a full load of 21,000-pound bombs onto the Port Stanley runway. Operation Black Buck, as it was called, was followed by a further equally remarkable long-range attack against the Argentinian forces on the runway, Black Buck 2, again causing considerable damage to airfield installations and vehicles. Another Vulcan, equipped with 2 anti-radiation strike missiles, knocked out the main Argentinian radar on the islands in Operation Black Buck 5. Operation Black Buck 6, again a Vulcan, attacked further radar installations. Unfortunately, on its return journey, the refueling probe broke and it was forced to land at Rio de Janeiro. A week passed before it was allowed to leave again, and only after the RAF promised it would not be used again in the conflict. In early 1984, the last of the Vulcan squadrons, number 50 Squadron, was disbanded. All of the aircraft had now been taken out of service and either scrapped or ended up in museums or as gate guards. However, for the next 11 years until 1992, one Vulcan was to survive, based at Waddington as part of the RAF's display flight. This majestic warbird continued to thrill crowds at summer air shows. It served as a constant reminder that this aircraft was once the world's first delta-wing bomber. Although it only ever saw action at the end of its long service career. The real value of this magnificent aircraft was that because it contributed a constant threat, being held at high readiness at all times, it played an important role in keeping global nuclear stability when it was most needed, giving Britain a dimension in international affairs that it would not otherwise have had. The RAF gave the last Vulcan a final tribute, thus marking the end of an era.
We're planning a round robin of everybody who in the Air Force have had anything to do with the Vulcan. So visiting all the old stations and the command headquarters where the aircraft's been operating from. It'll be a very emotional moment, that's for sure, but that'll be the end of an era.
The crews were
more than ready to do what was required of them, and so was the aircraft.